Now we're going to have a test of overall fit. Now, previously we found a way to test the individual coefficients of a regression equation using the t-statistic for each of the terms. What we want to do is we want to see if the model that we've developed with all the variables is actually a good model. Now we're not going to say how good, but we want to find out if the model basically does better than what we would call a null model, or a model with none of the terms in it, just an average. So what we're looking for is whether or not all of the coefficients in the model are equal to 0. So we set up our hypothesis test that looks like this. H0 is beta 1 is equal to beta 2 is equal to any number of beta n's is equal to 0. So this means our null hypothesis is that all the betas are 0. Our alternative hypothesis is that at least one beta is different. If all the betas are equal to 0, the model has no terms that are significant, and we call this the null model. So how do we conduct this test? We need to remember that a good model should have a small number of errors. We need to remember that a good model will have smaller errors. So we're going to examine the variance component in the regression model. First, we consider our actual y values, and if we calculate the distance of each observation from its mean, the formula is as follows. We have the sum of each of the individual y observations minus the mean of all the y observations squared. We add them all together. We're simply subtracting each of the observed values from its mean and squaring it and summing up those values. And this is called the sum of the squared differences. We're going to represent this as the total variation of the dependent variable y, which we're going to label as SST, sum of squares of the total. Now that we have this, we want to see the variation in the errors, or in the residuals. So we're going to do a similar formula. We're going to take each of the observations, and we're going to subtract the individual predicted values, and we're going to square it. We add those all together. And this will give us the squared distance between each actual y observation and the predicted value. This is called the sum of the squared errors, and this represents the variation of the residuals, and we're going to call this SSE. Now, remember that we have three parts to a regression. We have our independent variables, our dependent variables, and the residuals. The variation in the dependent variables should equal the variation of the independent variables plus the part that isn't explained by the independent variables, known as the errors. So if you remember our regression equation of y hat equals beta 0 plus beta 1 x1 plus beta 2 x2 plus a number of beta n's plus our error term. The error, or the variance in the y side, in the y hat, is going to be equal to the variance accounted for by the regression pieces plus the variance in the errors, because that's what we're saying the whole equation is going to be equal to. So therefore, the following should be true. The sum of the squares of the total is going to equal the sum of the squares of the regression equation plus the sum of the squares of the error. Since we already have calculated SST and SSE, SSR is easy to compute via simple algebra. SSR is equal to SST minus SSE. At this point, we have all of the variation in the model accounted for somewhere. The explained variance in the model by the regression, which we'll call SSR, and the variation not explained in the model, which is the sum of the squared of the errors, or SSE. Adding these two will give us the total variation in the dependent variable, which is SST. So now, if we have this, we're going to set up a hypothesis test, and we're going to use an F-statistic to compute the p-value. Again, Excel will do this automatically for us. But let's understand how this works. The null hypothesis for the test of the overall fit is on the right, where all of the betas are equal to 0. And the alternative hypothesis says that at least one is different. So we're going to compute an F-value. In order to compute an F-value, we need two additional measures. We need something called MSR and MSE. Now, MSR is the mean sum square of the regression. Think of this as the average sum of squares of the independent variables. So you're taking the SSR and dividing by k, where k is the number of dependent variables. The mean sum square of the errors, or MSE, is similar to MSR in the sense that it's the average of the errors. But what we're doing here is we're dividing SSE by n, which is the number of observations, minus the number of variables, minus 1. So to compute MSR and MSE is pretty simple, just using some simple algebra. Our F statistic is just the ratio between the MSR and the MSE. So our F statistic is equal to MSR divided by MSE. So let's recall earlier that we had stated if we want the errors to be as small as possible and we have a good model, then the mean square of the errors will be very small as well. And if that's the case according to this ratio, then the F statistic will be very large because the MSR will outweigh the MSE. Again, remember, if the MSR for some reason was 10 and the errors were 1, our F statistic would be 10. If our errors were even smaller, let's say 0.5, then the ratio would be 10 over 0.5, which would make the F statistic 20. So the smaller the number of errors, the smaller MSE will be, the larger the F statistic will be. When the F statistic is large, generally over 3, the p-value will be less than 0.05, and we can reject the null hypothesis and state that the model has good fit. In other words, we would say, more specifically, that at least one beta is different, and therefore it's better than the null model. So let's look at a sample here. Again, we're going to use the same example that we had with complaints and sales in the model. But as we can see, we've used Excel to calculate the ANOVA table, which is going to have our F statistic. We'll set up our null hypothesis, H0, as beta 1 is equal to beta 2 is equal to beta n equals 0. And our alternative hypothesis is that at least one beta is different. Now, the area shaded in blue shows us where we get the information to conduct our hypothesis test. And as you can see from the table, the MSR is equal to 278 and the MSE is equal to 4.76. If we calculated this ratio manually, we would get 58.51, but Excel has computed all of it for us. And not only that, it's given us the p-value as well of 9.5 times 10 to the negative 10th power. So since this value is much less than 0.05, we could safely reject the null hypothesis and state that at least one beta is different, and therefore the model has overall fit. A few notes of importance here. Number 1, Excel and all other statistical applications compute all the values for you, so you don't need to calculate them manually. But it's good to know what they are, and it's good to know why they work. There are some cases when the t-statistics of the model are small, but the model has overall fit. Thus, it's good practice to conduct the F-test. However, these cases are not that common and require a deeper understanding. The F-test is computed in a table called ANOVA, which stands for Analysis of Variance. The ANOVA tables are used quite often to compare variance between the sets of the models. And if you remember from a previous module, we had looked at computing the variance of one variable over the variance of another variable using the F statistic. And that's what the F statistic does. It calculates and compares differences in variance. And we're going to talk about ANOVA a little bit later in another module. Now, although the model may have overall fit, it does not mean it's good for use. We say it has utility, which means there is some use for it, but how good, it doesn't tell us. And it doesn't tell us how much utility we get from this. Other measures such as R-squared will give us a better idea of how good, and there are other statistical measures that will do that as well.